couple years ago, Stanford did the famous ALOHA kit, where they took 4 of our arms and made a machine learning platform out of it, and it went crazy viral. And so overnight, we were quoting like crazy, and a new market emerged, and now we're rebuilding the company essentially to serve this market that's kind of adopted us. A lot of people think we might be like an overnight success, but like most overnight successes, the company was there for 20 years before it happened. Trossen Robotics was founded in 2004. It was founded with me literally sitting up at 3 a.m. in the morning with a brilliant idea and decided I wanted to start a company. Back then I was a programmer, and I wanted to build some like virtual reality experiences where you could have like a fan and like vibrating motors and lights that would change and things like that you'd be immersed in, almost like a video game. But I'm not an electrical engineer, so I didn't know how to do that, but I was a programmer, and I thought, wouldn't that be cool if I had components I could plug into the computer and then control those, and instead of being on a microprocessor, my PC is sort of my brains of the project. And literally like sat up at 3 a.m. and I was like, that's brilliant. And I started jotting things down, and I can make motor controllers and servo controllers and take in different types of sensors and things like that. Well, turns out someone else had the same idea, and they had it about a year earlier, and they're called Fidgets. And that's physical widgets, spelled P-H-I-D-G-E-T-S. And they're a Canadian company. And so I called them and managed to convince them to give me some free stuff, and I was going to start a store for them in America. So I started fidgetsusa.com, and that was the start of the company. So when you have all those components, you have to then buy the motors that go with them, then you buy the wheels, then you buy the brackets that go with them, and the sensors. And the store just naturally grew and moved towards robotics on its own. It was never sort of a grand plan for that. It just sort of happened. I was just following my passion and things I was interested in as like a nerd and a DIY person myself. And literally one day I woke up and was like, I have a robot store. And it was never planned. And so we started collecting more and more robots from anything from mom and pop shops all the way up to big companies like iRobot, and filled the store in that way. We served the hobby industry really strongly, and education. And we eventually got into building manipulators. And then researchers started adopting us as well. And that was basically the first 20 years of the company. And then a couple years ago, Stanford did the famous ALOHA kit, where they took 4 of our arms and made a machine learning platform out of it, and it went crazy viral. And so overnight, we were quoting like crazy, and a new market emerged, and now we're rebuilding the company essentially to serve this market that's kind of adopted us. And so it's kind of a right place, right time. A lot of people think we might be like an overnight success, but like most overnight successes, the company was there for 20 years before it happened. So when you talk about pain points trying to serve the machine learning market, the very first one was servos. So when the ALOHA kit came out, we were still on our legacy kits, which were driven by robotic servos, which are basically professional hobby servos. They're small, there's large gear trains in them, they're very expensive, and they didn't exactly work well for this industry. People want low gear trains, they want torque transparency. Right as this stuff was coming out and getting popular, all of a sudden these new QDD motors started hitting the market in Asia. And actually there's some Asian companies that got the jump on us and started making arms that were even better fit for machine learning. And so we scrambled like immediately trying to figure out like who were the suppliers that make the best servos, how do we get our hands on them, how do we build around them. And right there is the 𝗿𝗲𝘃𝗲𝗹, which is our first machine learning arm that was built properly for this market.
Yeah. I mean, beyond basic market dynamics, which is give me as much as you can for as little as possible, our function is oftentimes finding consensus within the industry. And so, especially when it comes to researchers, they're all over the place. One wants suction cups on the end, the other wants to hang it from, a jig and have it pick grapes and things like that. But for us to have a really great platform that's flexible, we have to kind of come up with what's the majority of people asking for. So payload increases were the largest thing. Also, the ability to get deeper into the drivers of it, being able to adjust parameters.
Yeah, I mean, there's a lot of demand around the servos, right? Because a manipulator, it's basically servos, right? There's a servo in each joint, and that is 99.9% of the arm. The rest is just linkages. They're just brackets, right? So there's a lot of attention being focused on answering people's needs with servos. And so you want torque transparency, which means low gearing. The other reason they want that is so that you can sense if you're hitting something, because machine learning models like to destroy things. They don't know when they're hitting something sometimes, and the torque transparency helps that. The problem with that is that the lower the gearing, the weaker the motor, right? So at the same time, they're saying, well, we want to pick up 1 kilogram, 2 kilograms. The motors are overheating, and then we have to pause, right? And the worst thing in the world when you're doing research is downtime, right? And especially if you're doing data collection to sell data to researchers. So it's all about the servos, right? And so we've worked with different vendors and gone through different designs. We're working on the next generation of arms, and we're going to make our own servos. So we've gotten a lot of feedback from the market, and we know what people want, and it's all about customizing them. Well, for us, it's difficult if we're buying them from someone else, because you got to try and convince a vendor, hey, this is the next servo you should make. And they go, well, think about it. Or if you convince them, they'll be like, oh, it's 2 months to get it to you. So as a company, we've had to basically get lower in our tech stack so that there's more ownership in-house. And we're going to talk later about how we're also going upwards with the data pipelines and cloud development. So it's basically, we started in the middle by sourcing servos from one place, and then making our own brackets and building the kit, and then doing some software on top of it. And then we're expanding in both directions. And you have to, because we have to answer the needs of the market quickly.
Right.
Because there's no one more impatient in the world than a researcher.
And we're up against a lot of, companies that are able to allocate, resources, whether that's talent or money, very quickly and iterate. So, if you look at the research market, every 12 months, there's typically a paradigm shift in what we need to be able to provide for them. So we have to be extremely agile about things. We can't make huge, large orders of servos. We can't commit to 10 million servos,
Right.
because we know that, these will be replaced relatively soon.
Right. I would even argue it's 6 months.
Right.
Like if you don't have a new product or a major update in 6 months, like you're not going to be alive in 12
Right.
months. Right. Like the cutting edge on this stuff is moving so quickly, and the price points are coming down very quickly. And one of the pain points for us is the price points, right? Because people want an ROI on this, and those that are creating data farms have to get this stuff cheaper in order for it to make sense. And we also serve startups that are trying to figure out what is the next great application of this technology. And if it's a $10,000 arm, they can't do it, right?
Right.
So they're investing with the hopes that the hardware gets cheaper. Right, and they just want it as low as can be, and it's like hardware is always a race to the bottom, right?
Right.
And then also one of the reasons that we need to expand what our product line here as a company, so that we're layering in the software, we're creating the kits that the arms go in, we have the controllers inside. We have to expand our stack, because the servos and the brackets are just going to get cheaper and cheaper, and if that's the only thing you make, you're going to be in trouble, and arms are going to come from Asia that undercut you. And the market will buy them if you don't have features around them. And so we as a company are very fearful of that. So we're expanding the stack.
Yeah, I mean, the largest value that we provide is we save people time. The more that we can do relatively agnostically to fit a large number of researchers, the better our products sell. So, if we can provide support, if we can provide software, if we can provide services, and augmentability, 3D printed parts, and we give you the design files for them, so you can, to your heart's content, make which end effector you want. It makes it easier and easier to sell. Basically, there's no excuse. Even if I have an option for an arm that's $2,000 less, but I need to take 2 more weeks to integrate it and research the drivers, and what about the computer, and now I need to figure out all the dependencies there. one by one, we're trying to solve these problems
Right.
for customers.
Right. And we were talking earlier about the history of Trossen Robotics and what our niche is, and that is we've always provided like a solution, a research lab in a box, right? And so we don't just sell the servos or an arm that's just a collection of servos. We put great pains into adding our controllers in there and building APIs around them and adding in the Hello World software. So traditionally, like let's go back 15 years, like we did sell a kit, and it was you'd assemble the arm yourself. You would get a batch of servos, you get some brackets, you go online and you read the guide, and you'd spend 4 to 8 hours building the arm, right? Well, we started learning that if we pre-assemble the arm and we charge more, which is great for us because we get more margin, those actually sell because researchers do not want to sit around building the arm. They want to be up at the application layer, they want to be doing fun stuff, they want to be putting smarts and behaviors into the robot. They don't want to mess with the hardware. So the niche that we found to stay alive, while a lot of other companies, came and went over the years, is that we always focused on creating a full kit, like a full set of solutions. So the first step was we assemble it for you, easy, right? The next step was we started adding in, ROS Hello World stuff, which you could speak to, right? We had, half a dozen to a dozen programs that would work right out of the box, and then you could start altering from there. And then we started creating these sorts of kits, right? And so Stanford is the one that figured this out. We don't get to claim that at all. Right. 4 arms and that sort of setup, doing the collection with the cameras and all that. But we watch the market. We see what is successful, and then we figure out how to integrate everything into that. So that is sourcing cables, cameras, computers, and then we happen to make the arms ourselves, right? And so now people are demanding that it works with machine learning models right out of the box. And so it's it keeps evolving and more gets added in. It's like when you get a luxury car, you get the latest things that it comes with, like intermittent windshield wipers at a time you paid extra for, right? Electric windows, you used to pay for that. Now it's a default in the car. Heating and air conditioning once was an add-on. And it goes down to the base models, right? So anytime new tech is evolving, that's what happens. It becomes an expensive feature, then it becomes part of the base model. And the kits that we make for researchers have done the same. Like you used to assemble it. Well, now you don't assemble it anymore. You used to have to figure out your own APIs and your own drivers. You don't have to do that anymore. Right. Well, maybe a little bit still. So the next generation, we're going to be solving that as well. And that's just the natural progression of the technology.
Yeah, I mean, think of it like a cargo van, We make it so that you can make it your own, but we give you a lot of the things that you need with it. Good gas mileage, a lot of space, do the headlights come on? So if you just equate that, that's going to remain our mission, to continue to do that. And as we get through the rest of this conversation and all these other things, it doesn't matter how small it is, down to, the strain relief of a cable or, making an advanced controller. We're just taking what we can do, and if we can meet consensus on that, we'll bake it into our products.
As I was talking about earlier, our job as a company is to create out-of-the-box solutions. And so that means adapting to the new technologies that the market needs. And obviously the data collection and the APIs and the data pipelines are something we had to add into our products in order to accomplish that. So that's his area. I'll let him talk about it.
So earlier when these kits were introduced by Stanford, we were using ROS-based pipelines for data collection, which was purely based on Python and ROS. And what we saw was it has its own bottlenecks and it was not widely adopted. Later, like in 6 months, we saw the rise of Hugging Face and the LuRbot framework, which was used for data collection, which was actually meant for robotic machine learning and vision language action models. And they had tighter integration with action chunking transformers, diffusion, and all other policies that researchers usually use in their experiments. So what we saw was like, if we try to integrate these arms with that framework, it will be widely accepted by all the researchers, and it will become easier for them to like use our hardware without having to spend a lot of time writing the code and the software for integrating these hardware into their pipelines. So that's when we moved from our own custom software for data collection to something that was widely adopted by other researchers. Then what we saw was integrating our own hardware with all these third-party applications makes it easier for researchers to go whichever direction they want to. So we added our Trossen AI arms into that framework, and the data collection pipeline was way easier, and it was way easier to train something that you need and create your own benchmarks so that you don't have to go ahead and create a whole machine learning architecture from scratch, because action chunking already exists, so you don't have to recreate something. So we save a lot of time for the researchers so that they don't have to recreate something for their baselines, and they can like innovate and create new stuff rather than reinventing the wheel.
Right. So can I jump in on something? Yeah. Hold your thought on that. But this speaks to just a bigger thing in business. This has nothing to do with robotics even, or the space we're in. A company is basically there to solve problems for someone else. That's what a product is, right? Through either your product and or a service, you're solving a problem for someone else. And the better you can solve a problem, the more success you have as a company. The more product you sell, the more people come and say, solve my problem and I'm giving you money in return, right? That's the core of a business. So what you're talking about is they had a problem with okay, I got the hardware, but now what do I do with it? And I got to go figure out how to plug all the pieces together. Mm-hmm. And so the more that we can solve higher points in the ecosystem for them, the better it is.
And then what we did was like, we saw these features like easier access to data, how they can push data sets to a cloud infrastructure, how they can access it, how they can add models to the existing infrastructure. And then it was way easier for researchers to work with that. But later we found that there are a lot of bottlenecks that exist in that framework because it was purely Python based. And we were using some USB cameras at that point, which were real-sense cameras. And when you connect multiple cameras to a single system, bandwidth is not enough for the data set to actually hold up to 4 cameras, and the control FPS drops. So one kind of solution that we came up with was, rather than using Python as the backend, we can go and use C++, which is like meant for multi-threading and multi-processing, and it becomes way easier to manage the control frequency, which is very crucial when it comes to data collection and keeping your data sets clean. So now that we are moving towards creating our own SDK, which will have similar features that the researchers demand for, and we are also creating our own cloud infrastructure that will let them push data sets, access it easily, and share it with the community if they need to, because we are looking for like an open source ecosystem for VLAs where people can actually share data sets and not keep everything to themselves. As Mark said earlier, like the only problem with ChatGPT and the state-of-the-art VLAs that we have is like ChatGPT has access to the whole internet, and they can train on the data set that was created by humans throughout the history. But we don't have data sets for robots that have actions and images. So open sourcing every data set is kind of the way to go. So all these different labs will collect data sets and push them to a cloud infrastructure, and everyone can access it from there. That's what our data pipeline right now looks like, and that's the shift that we are looking at. So the way we integrate state-of-the-art models with our hardware is like, as we all know, like when we started, it was action chunking transformers, which came from the ALOHA project, and it was like the first state-of-the-art model that was out there like 15 months back. So the goal was to add transformer architectures to solving imitation learning kind of a problem, which was new at that point of time, and that's why it was like a big deal, and it saw such a huge demand in the industry, because it changed the whole, like the world of how imitation learning works. Initially, there were like papers like RT1, RT2, which was like talking about how you can encode text and actions into like architecture and then map, like predict sequences. And what we have seen, like when transformers were introduced, they were the best at solving sequence to sequence mapping questions, which is like getting in text input and then predicting the next text output. So that is how ChatGPT initially used to work. And then efforts were made to use the same kind of architecture in actions as well. So that's where we saw action chunking transformers. And then for the mobile robots, we saw using action chunking transformer plus, which was just adding more extra modalities to the base and moving the robot around and solving tasks. And later what we saw was like this was like used in other VLAs as well. Like when we came into the VLAs came into picture, VLAs are vision language action models, which take in vision, like the camera inputs, the language input will be the text, that the task that you wanted to accomplish, and then it will predict actions as the output. So what we saw was like the initial VLA that was like very popular was OpenPy's 𝗲𝗃𝗃𝗃, which changed a lot of things. Like it was one single like a generalized foundational model that was used by like different robots. Like you can have multiple robot modalities and it will be solving all the tasks like folding laundry, taking out toast out of the toaster, putting eggs in the carton, and all those problems were solved using a one single machine learning model. And that was a whole different, like it was a very big step in terms of machine learning. No one ever solved those problems earlier using that kind of precision and accuracy. Tries were made using, there was a paper called 𝗿𝗃𝗃𝗃, which was like for solving such kind of problems, like using different modalities of robots like drones, mobile, quadrupeds, manipulator arms, and taking all those and solving problems which are related to those special robots. Like for a quadruped, it will be walking or navigating through a maze. For manipulator arms, it will be like picking up and placing things, and all and more complex tasks. But those papers didn't really solve all the problems that 𝗲𝗃𝗃 was able to solve. And after 𝗲𝗃𝗃, we saw ALOHA Unleashed, which was again from, it was an initiative with Stanford, like the same researchers that worked on the original ALOHA paper and Google DeepMind. And they were able to solve a very complex problem that was tying a shoelace using the ALOHA arms, and which required like immense amount of compute, immense amount of data. And when you read through the paper, you'll see that it's not really possible for a normal researcher to recreate something like that, because it's Google DeepMind and they have a lot of resources.
Deep pockets.
Yeah. So what happened was like, even when ALOHA Unleashed was released, it wasn't widely adopted because the compute was immense. Like no one can really recreate those results. So, and then we saw 𝗲0.5, which was released a couple of months back, which was a successor for 𝗲0, which solved problems like segmenting tasks. Like each task was segmented along with the knowledge that's required for it. And it had better performance, smoother actions, and better generalization. And because I'm talking about OpenPy and the work they are doing, they are able to launch all these state-of-the-art models is because they have the best researchers that are in the industry right now, and they are leading and this whole VLA scene right now. So what happens is, what we try to do is let people integrate our hardware into this software ecosystem that we have. So right now what we did was we integrated our hardware with the OpenPy repo so that people can directly use the base models that are created by Pi and use our arms with that. And they get access to the data sets as well that we collect for these experiments. And then they can fine tune their own models using the base models that are given out by Pi. And then they can accomplish tasks that are suited for their experiments. Like any company can now get our hardware, use OpenPy in the background, and fine tune it for their own tasks, like maybe doing kitchen work or cooking food and anything of that sort.
Some of the challenges we've had in hardware aren't the things you'd think it would be. It's actually like getting the cables right and the grippers right. Controllers need to evolve, camera selection with vendors need to evolve. I can talk about this hardware stuff in a minute, but I think people would be curious to hear the challenges your team has dealt with on the controllers and cameras.
Yeah, one of the main issues that we see with our kits is, customers want to be able to capture a lot of data at very high rates, at very high resolutions, very reluctantly. And some of the biggest issues with that is with the camera hardware itself, or at least the legacy camera hardware. So previously and currently we use a lot of USB-based cameras. And while those are great for 2 to 3 camera setups, maybe if you're just pulling at like 360p, like that's all great and good. But once you get to 4 or more cameras and you are pulling high resolutions, you are pulling depth information from these cameras, then we start to reach the limits of the USB protocol, reach the limits of the actual like ingestion of the camera data at the computer level. And we are looking at a lot of alternatives. Some of those alternatives being, instead of using the USB-based cameras, we instead use the GMSL2-based cameras. So we have the D457 from RealSense, we have the 𝗧𝗵𝗲𝘃𝗲 from Stereolabs, and we're seeing a lot of good results with these cameras, and we're seeing a lot of the industry move away from these USB-based cameras because of those limitations.
Distance too.
Distance too, yeah. You can only run USB over very, very short distances. Maybe a meter is good. Maybe you can get 2 meters out of it. But these GMSL2-based cameras can go very, very, very long distances.
Yeah, so when you're creating an actual kit where the cameras are mounted around a big area and you're making large work cells, which will get even bigger when you have a humanoid torso type shape in there, the length of the cable matters.
Right, yeah, it's great if it's just mounted to the end of the arm where it only has to run a little bit less than a meter, but you can even see on these kits, like behind that Trossen logo, there is a camera, and you have to run that cable all the way down those legs and then into the ingestion computer.
Yeah. Which introduces another problem, which is cable flex, right? So traditional, what is it?
GMSL2.
GMSL2, whatever. I'll get it right one of these days. Traditionally, it's very stiff cables because they use them in automotive, right? And industrial. So they run a cable and they pin it down and it doesn't move. Well, our stuff moves. So we're actually dealing with vendors trying to customize cables that are flexible and don't break down as often as they do traditionally. So we could like get down to material science levels as a company, and it's kind of fun, but it's a challenge, right? Like every time you move to something new, or our client base demands something new, it causes another problem somewhere else.
Yeah, and it's, again, we don't have tens of millions of dollars to define a new standard. It's being adopted from a completely different industry because it's the only alternative out there that's better.
Right, and then talk about the boards that you were running into.
Yeah, I mean, just
like trying to develop boards.
Trying to, have a way of getting that information into a x86-based computer. I mean, you think it would be easy, but it's not, because it comes from this niche market. Like if I'm a developer using GMSL, I'm either in a very expensive automation solution or I'm in a automotive solution where I can afford a $5,000-$6,000 capture card, and then an entire card's being put into and driven 50,000 miles and testing that out. But when it comes to the bleeding edge of robotics, I mean, these are researchers that have budgets, and they look to a company like us to solve that and do so affordably. And so where we have to go is find partners. So as good as a hardware partner we have to look for hardware partners as well. Working with, the NVIDIAs, the AMDs, the Intels of the world, to be able to deliver these hardware solutions for these customers. So, I think in the next 12 months, GMSL will be relatively affordable, can run on x86, and will likely be adopted by robotics. And we'll see, USB kind of be this smaller player when it comes to CV.
Right, and Mark himself has been like calling vendors all over the world, trying to find someone who will custom make a GMSL2 capture card for x86 and a computer for less than $1,000, right? So it's funny how often we think, oh, that'll be easy, we'll just connect these together. Wait a second, a critical piece doesn't exist yet. And so we have to go and invent it or cajole someone else to invent it in order to solve these problems. And we run into that all the time because robotics is, metal brackets and servos and controllers in the servo and controllers in the arms. and firmware that's on those and special chips and then data pipelines and then cloud services. We touch everything in robotics,
Right.
which is exciting and fun because we don't get bored. But
Yeah, and as
there's-
soon as my problem ends, I found the card and I found the right price, it begins a new problem for the software team. Now they need the drivers to work. It has to integrate within our software stack. It has to meet our benchmark expectations. So,
and do it all for $100.
right, exactly. But, you know, those are always fun engineering challenges because we are at the forefront of this industry. And, you know, we lead by introducing these new technologies at a reasonable price. And that's what drives, or ultimately will drive commercialization, right?
Right. What about our controllers? You guys have been hard at work shrinking our controllers and getting all the features on those.
Yeah, so another one of the issues that we saw with like the previous generation of ARMs, again, it was like surrounding USB. So the communication between the control PC and the ARM relied on USB protocol over RS-485. Instead, we have moved over to an Ethernet-based system. So instead of relying on the flakiness of the USB connections, you instead have this very sturdy, very reliable Ethernet-based protocol that allows our custom driver to talk to the firmware that is on this board. We're also introducing a lot of other really great features. So we're running inverse dynamics on these controllers. We are running safety algorithms on these controllers. So if anything goes wrong, the ARM goes into a safe stop state instead of crashing due to gravity or experiencing just very strange or unexpected behavior. We're adding some hardware synchronization to these controllers as well. So, these cameras have hardware synchronization where you go to the hardware level in the cameras and request a frame, and it gives you that frame at that timestamp. We're doing the same thing on this controller. So you know precisely to the nanosecond when all of the last records were received for each of the joints. So we're packaging that up and then saying that, which allows for data synchronization, which is another very important thing in these machine learning models.
Yeah, and so there's a feature did a client ask for that, or did we think that up?
A client did ask for that.
Yeah, so a client said, hey, they're just constantly pushing the envelope. Can we have this too? Can we have this too? And like, it's funny because I call it like the 4 stages of grief for engineering. We're like, why you got to ask for that? It's too much. To maybe I don't have an idea about that. To them being excited, oh my God, this is this is great. To look how smart we are. We did this, right? And you go through these 4 stages
Right.
with these requests, but we're really stepping up the game. So like a lot of our competitors who sell ARMs, like you literally get a CAN bus to USB dongle, and that's it. That's your ARM controller. Screw you, you're on your own, right? We have an actual ARM controller that's on the board that solves all this. And then you guys are doing sort of load balancing between the actual servo controllers and the board controller, correct?
Correct. Yeah, so because we have control over the entire hardware stack, not only do we have these controllers that run all the safety and inverse dynamics algorithms, but now we have control over the motor drivers that will live inside of each of the joints. And that allows us to do some really fancy things with how we run our estimation and control algorithms on our motors, to even how we talk between the ARM controller and the different motor drivers. That allows us to get way more efficiency. It allows us to estimate our state way better, allows us to have much tighter control, and then allows us to communicate at much, much, much higher rates, eking out even better performance.
And so what's that, in layman's terms, what's that do for the customer who's the people doing machine learning model training?
They have ARMs that generally perform better. The quality of their data is much higher. They are receiving that data at higher rates. And with just general overall quality improvements, they get better machine learning models.
Yeah, so training models. It's going to come down a lot to where the industry has been and where it's going. So, like, for example, with ACT, on even relatively modest hardware, I could collect data, train the model within, maybe 10 hours, and then do inferencing on it. Then these large models come along like OpenPy, and, their hardware requirements are immensely more. So you see behind us, we made what's called the total workstation, because we got all this demand for people wanting to run OpenPy, and the minimum on there I think is like 16 or 24 gigs of VRAM, and that's just for inferencing. Not to mention they want to take in more and more data. They want to do it at faster rates, and so within 24 months we go from any laptop that's modest can work to now you have to have the bleeding edge, the most high performance of graphics cards and CPUs and 5th gen storage and 10 gig Ethernet, etc., to be able to do the research level things. And then we're seeing beyond that right now. So when you want to train that model, you can wait 80 hours on something like this, like a local edge compute, or you can offload it to the cloud, or maybe it's more like 16 hours. And the cost is interesting because it comes down to like, do I have the flexibility of just running for 80 hours and then let it go? Or do I want to cough up $100 for training it on the cloud? And how important it is for my timing and things like that. So we see, relatively a balance of wanting both, but I think really where cloud computing is going to come in is a seamless experience between edge and cloud, and a lot of that comes down to the software that's built on top of it for ingesting data, training models, storing them, and then doing inferencing. And each one of them has pros and cons as to what works better as either edge or cloud. But, Luke, you're building the cloud infrastructure right now, so you can talk best of, where edge computing, sort of the benefits of that end, and where cloud computing really takes over.
Yeah. We really see a vision here where you have everything running on the edge with regard to data collection and model inferencing. So with data collection, those are very compute-intensive applications, very storage-intensive applications. You are doing a lot of I/O operations with both peripherals and writing to the disk. Once that data is collected, then it can go anywhere. So it's either, like you said, you can train on a GPU that is, you can train
Just locally versus cloud?
Yeah.
Yeah.
But it comes down to like I said, it comes down to your patience, comes down to, how big of a model is it. At some point, it becomes too burdensome just to
Plus,
let
you
it
might be
run.
using other people's data, right? So you might want to tap into massive storehouses of data, which is only going to work on the cloud, right?
Right.
So again, companies like ourselves and Neuracore are trying to solve some of that by having storehouses and collecting this in one place, having your model up there, and that's where it's going to go, and it's going to get cheaper and cheaper to do, but also the data sets are going to get larger and larger.
Right. I mean, it makes a lot more sense for me to spend $5,000 a month for access to 4 or 5 H100s or H200s than it does for me to spend $300,000 up front, knowing that I could train a model and it fails and things like that. So that's the real advantage of where cloud computing is at. You get access to very high-end hardware, and you don't have to pay
You have
it
to keep
all up front.
upgrading it, right? 'Cause
Correct. Let them upgrade it.
Right. Spend $300,000 for it to be worth shit in like 6 months.
Exactly.
Right.
So, we absolutely anticipate that. It will just keep getting bigger and crazier. And, we're even seeing it in the compute space for cloud, where they're making specific ASICs for neural networking, or not neural networking, neural networks, yeah. Wildly different than anything that a GPU looks like, or wildly different than anything like a basic x86 looks like, to be able to compute these averages and the matrix multiplication that really goes into neural networks better than traditional, gates and switches.
I mean, to add on to that, one more thing, as Mark said, was like, depends on the models that we are trying to train. But again, let's come to the example of OpenPy or Pi0. There are two different kinds of training that go into a PLA. There is a pre-training stage and there is a fine-tuning stage. So researchers, like high-level researchers won't really touch the pre-training stage. They leave it to the pre-training base weights. But if you are trying to incorporate your own hardware into a whole framework, it's really important for your model to know how your robots look or what color they are. So you have to, at some point, have a pre-trained model. And the part where I'm coming back to the need of cloud training is because these models, like the pre-trained weights, require immense amount of compute, like A100 GPUs and 100 gigs of VRAM. And it's like, it's a lot of data that it's going to crunch at one point. And also hyperparameter tuning that's required for you to understand what works best for your model. So, I mean, you cannot just say that, hey, keep the batch size 8, have the learning decay to be 10⁻³ and you'll get your model to work one shot. It doesn't really work like that. You have to do some hyperparameter tuning. So you'll be running multiple different models at the same time with different hyperparameters like batch sizes, number of training steps. And that's where the cloud infrastructure really proves very important. So you can run multiple different trainings at the same point, and you don't have to wait for your resources to free up on your local GPUs. And once you have all of them ready, you can test them out on your evaluation framework, which will be your edge compute. So that's where really like the cloud outshines the local training part.
So, at Trossen Robotics, we're working on the next generation of our products. So as we mentioned, we're going to make our own servos in the next generation. We're going to come out with 3 different types of arms that are coming. We have a new 6th-DOF. We are going to revive the 𝗿𝗲𝘃𝗃 line, which is a stronger arm. And then we have our 7th-DOF, which are basically humanoid arms. So those are all coming. We're going to build entirely new kits and platforms like you see behind us around those arms. And then we're adding in the data pipelines and cloud services and continuing to partner with other people that are innovating. And we're going to solve a lot of problems in there. So like things like as low as like the cables breaking are getting solved, right? We're going to put in, hopefully some better technologies like slip rings potentially that will solve that. We're doing metal core grippers with overmolding on them so the rubber stops tearing. We are fine-tuning the motors so that they overheat less, and you can do higher payloads because everybody wants higher payloads. We're evolving the controllers that go inside so that you have way more access to lower level things that are currently locked off by using third-party vendors. We're solving the camera solutions and removing USB with that. We have some new form factors of things we're excited to release that we're not going to say yet, but that we think is going to help move things forward in terms of moving in a more humanoid direction. These are all the things we're doing, and again, it's to solve more problems at the hardware layer so that people can have fun at the intelligence layer. One of our, is it trademarked, the helping innovators innovate? Mm-hmm. Yeah, one of our trademarked phrases is we want to help innovators innovate. And so we supply you with the plumbing, the hardware that hopefully works right out of the box that you can be up and running. And we're just sort of furthering that goal and continuing to expand our tech stack to do so.
Yeah, and expanding to more customers. So we know as more industrialized customers get into the machine learning space, they want things that can prove test beds to go and pitch to their own leadership teams and saying, we think machine learning is viable enough in industry to be able to be commercially applicable. And so, again, we're following along. We're like a boat at the sails, just like everyone else.
Right.
But we're working with them. Be like, you need these, tools, hardware, and resources. Let's build them together. And then, once they tackle that, then we could even move into, the commercialization.
Yeah. Like if you want to ask where do we hope to be in 3 to 5 years, it's commercializing this, right? Industrializing it, because that's a $100 billion company, right? And wouldn't that be fun? But it's furthering the philosophy that we already have, which is having everything in a box for you. And so right now we're selling that to researchers, which have a room full of PhDs. The next market after that is the customers that don't have a room full of PhDs. So then you take the PhDs, you put them in the box, right? So we have an actual alpha program where you can do a pilot with us. If you're, let's say, a Fortune 100 company and you want to get into this, we will put people on site with the kits and work with your researchers that you do have on site and show you this is how you get into machine learning research and think about how this could roll out into your factories. So that's an expansion we see as a company, and nobody else is doing that. And we intend to try and tackle that problem next.